No discussion of induction would be complete without doing an inductive proof of a sum formula, because it's such a popular thing to prove with induction. So here's one that's very cool. It's the formula for the sum of the first n consecutive cubes. And it's cool because it relates to the sum of the first n consecutive numbers without any power. It's the square of that. And one thing we are going to need to assume that we know is that we know the formula for this guy. That's a famous formula, which you can also prove by induction, but that's one that I'd prefer to have people do as an exercise. It's n times n plus 1 over 2, and there's ways to prove that without induction as well, or at least to understand it nicely without induction. All squared. Okay, so let's do the proof. So base case, we expect that probably to be easy, and indeed it is. 1 cubed equals 1, just the sum of 1 squared. You bet. They're just both equal to 1. Okay. So now we're going to assume P of k. One of the things that I forgot to mention about the whole P of k plus 1 notation, I know people get confused. They often assume that that's a formula for a number, for a numerical quantity, and so they assume it's like equal to one side or the other of an equation you're trying to prove. It's a label for a statement, for a logical statement, for a whole equation, not just one side. So it doesn't have a numerical value. So we're going to assume that this is true for k, some particular but unspecified k. And I'm going to write it this way as much as possible because there's only one place where we really actually have to know the formula for the sum of the first k. There's probably a way to get around knowing that, but I wasn't able to think about it or find it without too much work. Okay, so now inside the inductive step, so I could have labeled this more carefully. This is the inductive step. Okay, to show statement the k plus 1 version of the statement, which is 1 cubed plus 2 cubed plus k cubed, and then add one more cubed. I'll put a question mark because I want to emphasize we don't know that. And then this is the sum up to k plus 1 all squared. Okay. All right, so the proof of that substatement, well, so we're just going to start with one side. And immediately we're going to use the induction hypothesis. This is why induction is such a popular thing to do as an example of basic induction to prove some formulas, because it's clear how this new case contains the old case. And it's all about the relationship of the new case to the old case that makes induction work nicely. Hey, there it is. Oh, we have a formula for that, the previous case. That is 1 plus 2 plus all the way up to k squared plus k plus 1 cubed. Okay. Alrighty. So now I want to show that this whole thing is equal to the sum up through k plus 1 squared. Okay. Well, just to be a little different, I want to show that you can sort of meet in the middle. So I wrote this out and used the inductive hypothesis already. Well, let's write this out as well. And if we can just meet in the middle, it'll be okay. I don't want to erase any of that stuff. Okay. Let's look at this guy. 1 plus 2 plus 3 plus, and I'm going to do something that's very, very common when you're looking at sequences and induction, is the dot dot dots. I didn't need to put the k here because it's pretty obvious what's the number right before k plus 1, but it can be very, very useful to put that in explicitly, especially if you're going to separate off the influence of that k plus 1. Okay, so that's something plus something quantity squared. So that's just all these guys, but only going up to k squared, plus just the k plus 1 squared, plus 2 times that sum times k plus 1. Okay, and now here's where we have to use, as far as I can tell, we really need to use the sum formula for this guy. So to save space, I'm going to cheat a little bit and put that in as a k plus 1 over 2. 2's cancel. Okay. and I'm getting this sum squared, which is going to match this guy, notice, right? Plus, okay, this is a k plus 1 squared, and that's a k plus 1 squared times k. Okay, so we have a common factor of k plus 1 squared times 1 plus, okay, that's just has a 1 times k plus 1 squared, and then has an extra k. Oh, hey, that's no more, no less than k plus 1 quantity cubed. Okay, so these are equal. Okay, I'm not doing great style in terms of where I'm putting things on the page just because my page is small. Okay, but I started from one side, got to something, started from the other side, got to the same thing. I could put this together if I wanted to as a chain of equalities. This equals this, equals this, equals this, equals this, equals this, but I don't really need to. So by induction, so that was the proof of the inductive step. That worked. By induction, the result is true. Ooh, it's going off, isn't it? For all n. Okay. So definitely, if you're learning induction, you're going to do some of these proofs, not because these are the only thing or the most important things you're going to prove, some formulas using induction, although they tend to be pretty important. It's because of this fact that when you look at the next case of a sum, it's always the previous case plus something hopefully relatively simple. And that allows you to at least get the inductive hypothesis in use right away, and then hopefully the algebra is not too bad. Here, we had to do a little bit more, but it wasn't too bad.